Okay, I'm going to talk about the 2D seismic imaging pitfall, which is out-of-plane reflectors. Seismic reflectors appear high on the section when imaging off the line or out of the vertical plane of the 2D section. So what we're going to look at here is a 3D perspective on two lines. This is a dip line here in Peru, and here's a strike line running this other direction. The strike line has nice flat reflectivity, and the dip line has these pretty gentle dips, but well, fairly steep dips, I'd say. So then you go up here, and then when you get to the intersection point between the dip line and the strike line, you can see that the image on the strike line is higher than the image on the dip line. And it's a fair bit higher. It's much worse down in the deep section. This fault plane here comes up, and it's got a much larger mist time between the two lines because this is coming at a different angle in the subsurface, which we'll look at in a minute here. Now note that in the footwall of this thrust, we've got these nice flat reflectors, and they tie. So we've got a nice tie in the footwall because these reflectors are horizontal, but the dipping reflectors are not tying. So let's have a look at this in a 3D perspective. We'll look on either side of this dip line, and then we'll rotate around and have a look at the high side of the dip line. Now what I'll do is I'll rotate the strike line until I get to the place where the angle of the strike line is oriented normal to bedding, or normal to the reflectors on the dip line. Because this is the out-of-plane direction that we've imaged those reflectors on the strike line. And you can see when we find that angle, normal to bedding, we've got good correlation top to bottom, and you can see there's the angle that we're dealing with, and the correlation looks good on both sides of that 2D line. So let's talk about what's happening here and look at this in a 2D perspective. Here's the dip line again. And what we're doing here is when we have a dipping reflector, we image that reflector with source, in this case, source and receivers off to the left. So with our strike line, even though it's pretty close to the crest of the structure, it's going to image that reflector from a little bit out of plane. So if I lay that strike line down over here, you can see the structure appears high on the strike line as compared to the dip line. But if we rotate it, we can take this large mist tie that we have, and if we rotate that section, now we've got this, here's the fault plane in the dip line, and then here's the fault plane along the strike line, and these are the reflectors in the hanging wall, and they tie quite nicely. So then we could use a method where we follow this, we map this reflector, and then we say, okay, that correlates to this reflector along the strike line, and we can follow over to the next dip line, and then we can be confident that we've got the same reflector on this line and then the next dip line over, because we've correlated by using this kind of the old school paper section method, or in this case PowerPoints. So just to conclude, 2D seismic data may image reflectors out of the vertical plane, but the reflectors will be high. Seismic interpretation software doesn't currently allow for rotating 2D lines out of the vertical plane. 3D visualization and old-fashioned line ties will help correlate events normal to the reflector. So we take paper sections, or in this case PowerPoint, we can correlate from dip line to strike line and then back onto a dip line, either on paper or in PowerPoint, and then we can be confident about the correlation from dip line to dip line.